section is covering it, please. So this is the points where we stopped yesterday. We sort of gave overview of two main non-adaptive localization methods in the INCAE and went through some of the properties in this conclusion, but we'll now talk about adaptive methods. So why there is need in adaptive localization methods at all? The first reason is rather obvious, because those methods are not adaptive. They should be set up by you, by hand, by trying different settings, see how a system performs. And these are very expensive and time-consuming exercises. For example, when you run geophysical system, you ask yourself many questions like, what's the minimal localization radius can be physically? Should they localize vertically or horizontally only? Should they use some uniform radius, or should it be different in different geographic areas, etc., etc. And in all honesty, in practice, the non-adaptive methods work very well, and it's really hard to beat well-tuned system with non-adaptive localization, even using uniform simple localization with adaptive methods. So if you run operational system, that's probably non-adaptive methods is the first option you should consider. So you should try to keep your system simple as possible. So the second so now we'll talk a bit about two adaptive methods which are in the literature. As far as I don't know much about applications which use them operationally, but maybe some systems do, just not aware of that. But the first method was put up by Anderson in 2007. It's very nice. Anderson put very nice statistical framework on the adaptive localization. So it works as follows. Let us have an ensemble of, say, 100 members. And let's split this big ensemble in a number of sub-ensembles, say in 5 or 10 sub-ensembles of 20 or 10 members. And let's independently calculate the gain matrix for each sub-ensemble. So each sub-ensemble will have its own gain matrix. And the overall idea is that if the gain which we get for a certain element of your state vector from a certain observation is the same across all sub-ensembles, that it's reliable, statistically reliable, and can be used as such. If the gains given by different sub-ensembles are different, then somehow we should reduce this gain, because what's the increment which it produces is not very reliable, because it varies across different sub-ensembles. It's not consistent. So formally it's done as follows. Calculates regression confidence factor alpha for each element of the state vector. This is done as follows. Take some element of the state vector and look what different gains in different sub-ensembles are for this gain. And then minimize this equation, this quadratic function. And this is the formal solution. Actually, the formal solution is that, but Jeff, for some reason, says that the alpha cannot go below 0. So I can't comment on that, whether this improves or not. I think Jeff is not very sure himself. So if we look how this works, we can see that this expression can be only below 0 and 1. So if all gain factors from different subensembles are all the same, then we get the alpha equal to 1. And if they vary a lot, then we start to approach 0. But obviously we can go even below 0. So and this may be considered as a sort of adaptive localization. So any say if we consider, say, if this is our spatial domain of our model, and we consider gain, say, we consider gain for this element, and say from that observation. There is no spatial relation between those two. Whether we should use this observation in updating this point or not. It's all done purely in statistical way. So this is nice because, say, when we introduce some distance-dependent localization, we make a lot of assumptions. But physically, for example, the observations may be related to the model state in this point, not necessarily in an isotropic manner, but in some weird way. Say observations in this point can obtain the model in that point, but not others. So, and this is actually the second reason why one would like to use potentially adaptive localization, because it doesn't need the distance measure between an observation and a state element. And for some observations, it's really hard to introduce such a distance measure. So that's the first method. And what we can say about this method, but it doesn't require distance measure between observation and state vector element, but it's theoretically consistent. And the only weak point of this particular method is that if you go into details, you see that it optimizes for subensemble. So, say, if you split your ensemble of 100 into 10 subensembles, then this method implies that the overall the actual sort of distribution, statistical distribution of gain is given by a small ensemble, sum ensemble. So basically it optimizes for sum ensemble. So and you don't want, say, if you have a small ensemble, say of 10 members, in practice we should use much smaller localization operators. So in practice, what this method is doing is that it may produce too strong localization than is actually needed for your bigger ensemble. Now, the second method was started by Craig Bishop and Hodis in a number of works, and Craig still continues this work now, and so he makes new modifications to the original formulation. But the overall idea is is quite simple. So this method is quite similar to what we saw in the covariance localization, with one modification, that the correlation function which it's using is a function of the correlation function of our system. What does it mean? I showed you examples of the covariance matrix in my previous lecture. So it looked like a square matrix with some diagonal and sort of gradually reduces to something and noise elsewhere, basically. That's for one-dimensional system. But instead of covariance matrix, we may look at the correlation matrix for the same system. And the difference will be that the values on the diagonal, instead of something, some different values. So in covariance, the diagonal values give you variance for each element. If we divide, if you normalize by this, each deviation by standard deviation, each element by standard deviation, instead of this, we get ones on the main diagonal. So this will be the correlation matrix, and this correlation matrix is visually can be quite similar to the correlation matrices which are usually used in covariance localization. But the advantage of this correlation matrix will be that for each system we will have its own correlation matrix, so it will become system dependent. So to think a bit about it, let's draw a scattergram between some two elements of the state vector. Say we, for example, observe ice concentration in one point, say ice, and salinity in another point. That's the scattergram I showed you before, and it may it can look completely different in completely different situations. But say we obtain something like that. What can we say about this? We can say, okay, we can see the dependence between two variables, and the correlation is very close to 1. So we are quite confident that this is the real dependence between those elements. Now, in some other circumstances, we can have a scattergram which, say, looks like that. And we can still have some regression, which is not zero. So, but what can we say about this situation? We can say, okay, it looks like it's very chaotic, despite that we have some dependence between the two variables. It's probably not very statistically reliable. So, how can we account to that? The correction of one variable, depending on observation of other variable, is driven by the covariance between the two elements. It's proportional to this covariance. So if you consider this relation as not reliable, we want to reduce this covariance. So maybe just simply multiply by correlation coefficient between those elements. Right? So that's one way. In this, if we did that, then we would simply use for rho just correlation matrix which corresponds to P. But in reality, this approach uses much more sophisticated techniques. It smoothes correlation matrix spatially, and raises each element into some powers. So in this way, it has lots of parameters to tune. But it's adaptive method because the correlation function, or as Craig Bishop calls it, modulation function, remains on the properties of the system itself. And so the conclusions for this method are as follows: that as the previous one, it doesn't require distance measure between observation and state vector element. We have observation, and basically we examine the relation, the scattergram between the observation and the state vector element, and make our conclusion. So it also has a lot of tuning to play with. Say, in some circumstances, for example, some fourth power can work best, in some other sixth power, in some other second power, so there's no common recipe. So, and so it's rather physically intuitive method, like I tried to explain. That's quite an intuitive approach, but it still remains ad hoc compared to this other method. Okay. So, any questions on the adaptive localization? So,
one thing is we've looked before at ensemble collapse. Do these methods help to avoid that?
Yes, all localization methods they reduce the reduction of variance achieved in the Kalman field, because effectively you assimilate for each element of your system you basically assimilate less observations, so you don't effectively assimilate observations which you consider irrelevant for this state element. So if you have ensemble collapse, you probably want to know the reason, and the first suspect is you have rank problem in your system. That the number of degrees of freedom in your data simulating system is not good enough. So you need to introduce some localization to match the physical system and your data simulating system. So yesterday we said that when calculating analysis in the INKF framework, when conducting global analysis without localization, the analysis is a linear combination of the forecast ensemble members. This means that if you have certain physical modes in your system, linear modes, in your forecast system, then your analysis system will contain exactly the same linear modes. So this is no longer true with localization, and so this can be demonstrated in simple experiments. For example, you can run the, say, as you saw with the linear dimension, with the linear adversions system I showed you yesterday, it is set up, for example, in such a way that from the very start, the dimension of the state is equal exactly to 51. And you can try to run rank deficient ensemble, for example, with 30 members, which you know cannot represent such a system, because it just doesn't have enough nodes. But if you run with localization, then over time you will see that we still get the RMS error going to 0. This means that the missing modes, the modes which were missing in your original ensemble from the very start, are gradually replaced through time via localization. So this process can be called sort of diffusivity of modes through the localization. And so here is one particular example of how this works. So in this particular example, we used with Peter Roque a series of experiments with the same linear advection model. And here the thick gray line denotes the truth. What we see in this chart is the Fourier spectrum of our system at different stages. So on axis x is just Fourier harmonics, and on axis y is power spectral density of each harmonic. So the thick gray line is the truth. The continuous line, just plain continuous line, is the initial spectrum of the system. On the top chart, it's the initial spectrum of the ensemble mean, and on the bottom chart is the continuous spectrum of ensemble perturbation, of anomalies, averaged or summed up over the whole ensemble. And this other line, with the continuous line with the dots, it shows us the spectrum of our data assimilation system, spectrum of the mean and spectrum of the anomalies after 500 steps of our system. And we can see that it basically matches now the true solution. And we also see that, say, in this case, for anomalies, it contains some modes, because we only use 25 Fourier harmonics for our system. It also contains some harmonics which are not in the system. So that's the downside of this diffusivity, that you can have something which is not physical yet. So we have some leakage into the area of big wave numbers, whatever. So this diffusivity, it's indeed can be associated with the dynamical inconsistency of the analysis which we talked yesterday after localization. So, but dynamical inconsistency is a bad way, but diffusivity is actually a good way. You know that your system shouldn't span the subspace of the truth exactly, because even if it's in slightly different subspace, it will gradually rebuild the necessary modes through the localization. So this you can see as a positive side of the localization. So it's conclusions on the localization overall. That's what you should remember from this talk are as follows. That localization in the NKF is an ad hoc modification of the analysis scheme. So even when localized, we continue to use update the equations from the Kalman filter. Although we know that our system after localization becomes strongly suboptimal, quite suboptimal, so maybe not very strongly. But when it becomes suboptimal, we know that these effects that should affect the solution, and particularly the equation for the covariance update, which comes from the balance of the second order terms, even with some modest suboptimality, this update can become entirely over-optimistic or not correct. Then one thing which you should remember very well is that one must use localization if the ensemble size is smaller than the model subspace dimension. We don't specify exactly what we mean by model subspace dimension at this stage, just leave it on the intuitive level. But if you have a physical system with with a number of degrees of freedom, and if your ensemble size doesn't match, you must use localization. Localization makes the analysis schemes suboptimal and therefore inconsistent, and sometimes strongly inconsistent in regard to the estimation of posterior covariance. Localization makes it possible to recover the model structure from observation even with a rank deficient ensemble. By rank deficient, we mean rank deficient in global analysis. Next, there are two main non-adaptive localization schemes which you should probably use in practice as a rule of thumb. If you need localization, just try some of these schemes. If for some reason you're not satisfied, or your system, you feel that you can't use this isotropic distance dependence localization, then probably you can look at the non-adaptive schemes, on the adaptive schemes. And these two schemes are mainly equivalent, and the ones we showed, we talked yesterday, the covariance localization and local analysis, they are mainly equivalent. And we have shown this formally in our work with Laurent Bertino, that can be shown actually analytically that in the case of if your analysis, if your update is weak in some sense, then these schemes are mainly equivalent. And should be chosen by algorithmic convenience. So choose whatever is more convenient for you. Here's some little chance. So with this, I finish the lecture on the localization. So if there are any questions.
Yeah, one question. So you say there are two main non-adaptive localization schemes, and one could probably add in the University of Maryland group's local ETKF as another.
Local ETKF is a very particular case of local analysis. You use local analysis scheme and you apply it to ETKF, and you call it local ETKF, nothing more.
So by localization you strictly mean the sort of Schur product multiplication of the...
No. Schur product. If you talk about Schur product, this means that we talk about covariance localization. That's the first scheme.
Yeah.
If we talk about local analysis, and if you look in the literature, then you see the first instance of sort of referring to local analysis in the literature in 2003 work by Emerson. But he used no smoothing, no special smoothing at this point. So yes, the LETKF is local analysis with ETKF, and that's all. So local analysis, as we told yesterday, is scheme independent. You can make your local analysis with any scheme.
Yeah.
So in this case, LETKF is nothing special.
Yeah, it can be local anything KF.
Yes, yes, absolutely. So in the past, in our system, we run local analysis with the KF. We don't call it local KF. Just local analysis.
Right. Right, yeah, I see that you want to make a clear distinction between localization and local analysis.
No, between covariance localization and local analysis.
Yeah.
Yes, those are two different approaches.
Yeah.
But as I said, they can be analytically shown that in some circumstances, in some common circumstances, they give mainly the same result. Then I will lecture here. At this point, it's this. So, as you may see, this lecture is called Miscellaneous. It's we will go through a number of different issues, and after I finish on those, I will talk about a number of more issues. So, but here's the overview. So, the maybe half of this lecture is devoted to inflation, to the ensemble inflation, which is another, not as big, but another big concept in the NKF systems, which everybody should be aware of. So, what is inflation? Covariance inflation or ensemble inflation refers to artificial increase of uncertainty in the state estimate. Right? So, if we see that our ensemble is starting to collapse, we may try to multiply our covariance by some factor slightly more than 1, like that, and hope that over time this will prevent our system from collapsing. For example, so the covariance inflation is commonly applied by simple multiplication of some factor, some uniform factor, either by covariance or by ensemble anomalies, which is basically two equivalent ways of doing that. The first use of covariance inflation in this form, I think in this form, but it doesn't matter. That's probably was in paper by Anderson in 2004. But if you look at work by Fan in 1998, it contains a very similar approach, which he refers to as forgetting factor. And when you apply it in this form, it's not slightly over 1, but it's between 0 and 1. And because we know that the two approaches are roughly equivalent, we can see that introducing inflation is physically equivalent to introducing some sort of how to say it in English, some time memory in our system.
Is rho just a single scalar function?
Yeah. So in traditional and simplest sort of implementations, which you probably should try first of all, it's just a single number, slightly over 1 in this case, or slightly less than 1 in this case. So, and there are other sort of minor modifications. Say, Ott et al. Use so-called enhanced ensemble inflation, which they introduce like that, where epsilon is some small, so they boost the diagonal of your covariance matrix by some small factor, or by some small number, and but it basically works in the same way, but probably in some circumstances can yield you a bit better system performance.
TR is the trace.
The trace, yes. So Anderson introduces an adaptive algorithm for the inflation, and as we told on one of the first two lectures, the traditional NKF is prone to ensemble collapse, and you can actually theoretically estimate what's the expected underestimation of the final variance is, and try to counter this with some inflation. So that's what has been done in works by Sacher and Bartella. And Evenson in 2009 in his book, and also in journal publication, introduces yet another adaptive scheme called inflation. We are not going to but the reason for the occurrence of this adaptive algorithm is that many people consider inflation as a really major thing in the ensemble data simulation. Say, Jeffrey Anderson in personal communication says that they say very typically they have inflation inflation factor values of like 50%. This means rho is equal 1.5. So that's huge inflation. Or somewhere people talk about inflation factors of 50, and I even heard of inflation factors of 10,000. So, and what does it mean? If we use such a huge inflation. What is your simulation process doing? For example, with the ensemble SVD spectrum. So the SVD spectrum can be considered as just distribution of variance of the system along the physical modes, say. And so if you have some forecast SVD spectrum, something like that, distributed among a number of modes, what happens after the data simulation? As we said, it's the filtering theory says us that theoretically the spectrum should become lower and flatter. So lower because we know that the variance always reduces in the data simulation process. And flatter because there is a theorem which says that if we sort our modes in such a way that the spectrum is monotonic, like I've shown here, then the actual reduction of each mode is also monotonic. So it becomes flatter and flatter all the time. So if you continue to assimilate new and new observations with the same ensemble, you can see that, like in linear regression model, you can see that your spectrum becomes flatter and flatter, and lower at the same time. So if you use big inflation factor, this means that your variance is a way too low, right? Say, for example, it becomes something like that, and you think that that's a way too low. It should be much bigger. So we try to boost it with inflation. And what happens that when you multiply by a scalar, for example, in simplest case, you just boost your variance, and the new spectrum becomes something like that. Right? So, and why can it be too low? So the question is because we are just over-optimistic. We over-assimilated. So we used too small observation error variance, or made some other assumptions. We have insufficient ensemble rank, and when we have insufficient ensemble rank, we become hugely over-optimistic. This is the reason why people can have inflation factors of 50 or 10,000, insufficient ensemble rank. So, okay, and but what the actual, say, if we set up our simulation system in correct way, what the actual spectrum actually should be? It probably shouldn't be as flat as that. It probably should be something instead of this black line. It should be probably something shape-wise between that flat and that steep, something like maybe that. So my point is that using big inflation, when using big inflation, you consciously use incorrect sort of variance distribution among the modes. So the recipe is, if you have to use big inflation think about your system. You're doing something wrong. Try not to over-assimilate. If you have, for example, to use big inflation, increase observation error variance to such a point that you don't have, that your increment becomes smaller and you don't have to use such a big inflation. So in this case, you will obtain better sort of system with better properties. So three reasons are listed in the literature for the covariance inflation. It's rank deficiency of the ensemble, nonlinearity, and spurious correlations. That's just in the literature, if you just read through the papers. And so you can generalize all those that by inflating cover ensemble, we try to compensate for over-optimistic analysis that doesn't take into account suboptimalities of the system. So, and I strongly argue that if you have really rank-deficient system, then correcting it with inflation is wrong. You should look at the fundamentals of your system. Look at the localization first of all. So, and so I put it as this. Rather than use big inflation, try not to over-assimilate with a suboptimal system. So, from another point of view, it's known from the extended Kalman filter sort of studies, and there are lots of them, hundreds and thousands. It's a big field, the extended Kalman filter, because the area of application is so big. That's this system also effectively require small inflation for stability reasons, and so there are even some theoretical estimates which link the nonlinearity of the system and the inflation which is needed for the stability of the system. And say if you try to run almost linear but slightly nonlinear system, like say Lorentz 40 system, 40-dimensional Lorentz model, in situation where you constrain it very well, you still need a small inflation. Why? Because you can run it for stability reason. You can run the system without inflation very well for hundreds of thousands of steps, and then at some point it just diverges, it blows up, and that's it. So and if you try to see what happens if I add very small inflation, you can see that the very small inflation helps prevent such situations. So you can also think about inflation as small inflation, like of order of 1%, for example, or maybe even less, as a factor which is necessary for the stability of the system. Right. So here's we talked other day that if you see that the optimally performing system, say in twin system experiments, if you know what the truth is, you generally try to match the ensemble spread and the RMS error in your system. And that's you, at the same time, obtain the best RMS error, the best performance, when those two values match. Say, and if you see that those don't match, but say gradually diverge in time, you can try to match them by adding a small inflation as a tuning parameter. And this is an example of that. That's from our with Peter Oak's work from on the DNK-F. So the upper graph shows the RMS error for some system. Actually, for quasi-geostrophic model, which is in the NKF MATLAB package, over a very long period of time, or over many runs, for some different schemes. And particular schemes, they don't matter in the context of this lecture. And the coordinates here are the localization radius, and the second is the inflation factor. Right? And so the best performance is this sort of purplish color, and then some bluish color. So you can see that's the area of best performance for each scheme was something like that in each case. And the ensemble size, we did this with ensemble of fixed size. I think it was 25 members in each experiment. And this lower chart actually shows not ensemble spread, but the difference between the ensemble spread and RMS error. So 0 here, the black color shows the situation when the RMS error and the ensemble spread match each other. And you can see that those basically coincide with the parameters for the best system performance. So that's just one illustration of this principle. Now, the conclusions about inflation are that covariance inflation is an ad hoc modification of the NKF. So we can some theoretical reasons for inflation are understood, but in general, it's an ad hoc modification. The inflation factor is usually empirically selected. Just choose one for your system. Don't be too much concerned. If it works well, then it works well. Just leave it there. It's often essential, the inflation, for preventing the peak ensemble collapse, as well as for the long-term stability of the system. And in practice, a small inflation can often have a substantial positive impact on the performance of the system. So now I will run two experiments which shows the positive impact of the inflation. The first experiment will be with the linear advection model, and I will first run it with exactly the same settings I did on the in the lecture about the schemes when I demonstrated that the traditional NKF is prone to collapse. So we run it. It's probably explaining two levels of this. First, run it with inflation, with no inflation. That is, the inflation factor is set to 1. So we just see this situation of the the ensemble collapse we have seen before, you can see that the ensemble spread reduces just too quickly, and because of that, the system becomes non-responsive to the durations. Right. So, now we ask what we can do. Can we counter this collapse with some small inflation? So I will run now the same experiment with inflation of 4% at each simulation, unity simulation side. Comment out this one and uncomment 4%. And we run the same experiment. So we can see that we haven't exactly matched the spread and the RMS error in this case. So, but they're very close, and we can see that the system is responsive, that the RMS error reduces over time, and if we continue to run this system forward in time, it will still reduce the smaller and smaller RMS error. So we see that inflation, in this case, small inflation, prevents ensemble collapse and tries and helps us to dramatically improve the performance of the system. And still, this performance is not as good as you will get with a better spin in this situation. Say, if you use ETKF, for example, or any other square root filter, you will get much better performance than this. But if we face some particular system which is suboptimal for some generic reason we don't know what, we can probably, there are a number of ways that we can try to fix this deficiency. And one of them is inflation. So the second experiment I wanted to show is with the chaotic Lorentz-Forty system. It's this one. So I will run it twice. First time with no inflation at all. And then this very small inflation for a very short period of time. And we'll just see if it makes some impact on the system performance. So what we can see here is that the ensemble spread is, on average, is probably somewhat lower than it should be to match the RMS error. So you see that not by a big margin, but just a bit. It's below this curve. And if you look at the output, you probably cannot see it, but I can see mine. So the analysis RMS error for the last 100 steps, it says to me the average analysis RMS error for the last 100 steps of this system is 0.18 something, say 1. And the spread, the ensemble spread for the same period of time is 0.1674. 1674. So you can see that the ensemble spread is a bit lower than the RMS error. So you can ask yourself, what happens if I try to match those? So, and when you introduce very small inflation of just 1%. So we run exactly the same experiment with big inflation, with some small inflation. So I think the RMS error and the ensemble spread match with say heels a bit, but on average it's fine. So if I look in my window, which unfortunately you cannot see it, then I can see that now in the last 100 data assimilation cycles, we have RMS error equal to 0.1801 and spread is 0.1875. I have to make a disclaimer that with these systems, to get some meaningful estimate for RMS error or for some other system characteristics, you have to run it for hundreds of thousands of steps. Because what can happen if your system is prone to some small instability? This can only be detected in very long runs. So very often, in terms of RMS error, the best performance is can be obtained for some settings of the system, but at the same time, for these very settings, system may be a bit unstable. So if you increase stability, you can decrease slightly the performance of the system at the same time. So this is not indicative. That's just a very quick example I wanted to show you here. But this is just a short example. Just take it as a example.
So it would be a good starting point to do a long run.
No, if you want to make, say, a publication, and you say say, I achieve with this system RMS error of that, the reviewer would probably say you need to do you should do million cycles at least to make this step.
But what I was meaning was before you do that million cycles, you want to set a system
yeah.
as well as you can. So you could use this, and then do the long run.
Yeah, you can tune it very quickly. So So I think we're about at the break, so maybe we'll stop this break. If there are no other questions on this issue. So.
Well, there is more comment on the question, and maybe you mentioned it, something, but Mark Bocquet has been looking at the problem of localization, non-inflation, taking into explicitly into account the size of ensemble, and then deriving, making a hypothesis or making as to the property as to what the corresponding sampling error must be, and then correcting for the sampling error that results from an ensemble given a size n.
I'm looking very forward to this publication, but so
what I know, you just presented that a few weeks ago at the EGU meeting. Yes, I don't even know whether he has written a paper. I think he has done.
No. Laurent said that he has submitted that.
Okay.
It's the review process is longer than he explained. So.
Any other questions? I think the coffee may have gone across to the other room, so I will fix that so you have coffee.
Do you need some help with that?
I might.
Yeah.